Hello students, welcome to the today's lecture of data structure, and today's we'll be discussing about floyd-Warshall algorithm. So let's see. So agenda for the today's lecture will be we'll be discussing what floyd-Warshall algorithm is. We'll see the working principle using an example. Then we'll discuss the algorithm, complexity, and the transitive closure. So let's start with floyd-Warshall algorithm. See, floyd-Warshall algorithm actually solves the problem of all pair shortest path. Okay, all pair shortest path means, for example, we have in the earlier lecture we have used Dijkstra algorithm to solve this shortest path problem. See, but Dijkstra algorithm, all pair shortest path means, for example, in this particular given graph we have node 1. Okay, we have node 1 and we want to find out shortest path to 3 to 4. These are the 4. Similarly, from node 2 to node 1, node 3 and node 4, and similarly from node 3 to node 1, node 2 and node 4, and from node 4 to node 1, node 2, node 3. Now if Dijkstra is actually used to find out the shortest path from a single source. Okay, so let's suppose my problem is to find out the shortest path between all pair of vertices. Then what I need to do is I need to apply this Dijkstra algorithm many number of times. In this case, 4 number of times. One is for taken 1 as a source vertex, another time like taking 2 as a source vertex, third time for taking vertex 3 as a source vertex, and fourth time for taking vertex 4 as a source vertex. So you need to apply Dijkstra 4 times. Another solution is to use the floyd-Warshall algorithm. So floyd-Warshall algorithm actually used to solve the problem of all pair shortest path. Once you apply it to a graph, directed or undirected, with positive edge weights or negative edge weights, it can be used with all type of graphs. It will give you the shortest path between all pair of vertices, right? So in this case, see, our basic approach in this floyd-Warshall algorithm is, for example, if there is a path from vertex 1 to vertex 2, okay, then let's suppose there is a direct path from vertex 1 to vertex 2. Now there may be other paths from vertex, let's suppose it may be from vertex through vertex 4, or there may be other path through vertex 3 to 2. It might be possible that this indirect path, which is through some intermediate vertex 4 or some intermediate vertex 3, may be having the shorter distance as compared to the direct path. Okay, so then we'll use the this indirect path using through some intermediate vertex. For example, in this particular graph also, if you see that from 1 to 2, if you see at the direct path, it is of weight 10. Okay, but if you go from 1 to 2 through intermediate vertex 4, see 1 to 4 the total distance is 1, and from 4 to 2 the distance is 2. So if you follow this path from 1 to 4, 4 to 2, you ultimately have to go from 1 to 2. Now if you use the direct path, the total cost is 8. If you use the direct path, means from 1 to node 4 to node 2, then the total cost is 3. So this is the basic idea behind this floyd-Warshall algorithm. Actually what we'll do in this particular algorithm is that we use for example in this case 1 as a middle element, and then find out the shortest path between every pair of algorithm using 1 as a middle element. Obviously there is one is the direct path and one is the path which constitutes 1 as a middle element, which is through 1. Okay, then similarly we calculate take 2 as a middle element, then we'll take 4 as a middle element and 3 as a middle element. So using all the vertices, taking them as a middle element, we'll find out all the paths. The basic strategy which used in floyd-Warshall algorithm, we call it a dynamic programming. Okay, in dynamic programming actually we have to we break problem into smaller problems recursively and will take certain decisions. Okay, so we'll see it how. So intermediate vertices are, see, we'll assume that all the vertices of our graph are numbered from 1 to up to some value n. It means the vertices of the graph are numbered. Okay, then given a path, any path p from vertex v1 to some vertex vm, if there is a path, okay, then we will call the vertices vk. Vk is from 2 to m minus 1. Obviously v1, the starting vertex is not there in the, and the last ending vertex is not there. All the vertices in between are called the intermediate vertices of this path P. Okay. Now the basic idea behind this Floyd-Warshall algorithm is that we'll consider the shortest path P from a vertex I to j such that the intermediate vertices are from 1 to k. See, we'll take k one by one. See, k will take all values actually. Okay, let's suppose this: if the vertex k is 0, vertex k is not an intermediate vertex on the path P, then dk is d of I j. Ij means this I vertex and j vertex. We are finding out the distance. Distance means the cost of the path from vertex I to vertex j is the using the previous vertex which we have visited earlier. If the vertex k is an intermediate vertex, then we'll find out the cost of this path from, see, for example, if we have to go from I to some vertex j, and we are using k as an intermediate vertex. One path is the direct path, okay, and another path is from I to k and then k to some j. This is what, so this is the distance from I to k and then from k to j. So these two distance we will find out. Now in either case, whether you are we can conclude from this that the distance from I to j, using k as a middle vertex, using k as a intermediate vertex is minimum of, see, in this case when we are not using k as a middle vertex, one distance, and when we are using k as a middle vertex. One case we are not using k as a middle vertex, and in another case we are not using k as a, we are using k as a middle vertex. So out of these two distances, whichever is minimum, we'll take that. Okay, because obviously we want the shortest distance to be find out between any pair of vertices, right? So recursively you can say that if k is 0 means, for example, this is distance between I and j, and k is 0 means you are not taking any intermediate vertex between them. You are talking about the direct path. Okay, that is the weight of the edge between these two vertices I and j, simple as it is. Now if k is greater than 1 means you are taking some intermediate vertex between vertex I and vertex j, then you will calculate this, that the minimum of distance between I and j when you are not using k as an intermediate vertex, and distance from I to k and k to j. See, distance from I to k and k to j, whatever is minimum in between these two, will take that values. Okay, we'll understand this by with the help of an example and come back to this again. Okay, now see this. Now we have to, given this graph, we have to apply the Floyd-Warshall algorithm to find out the all pair shortest path, means shortest path between every pair of these graphs. See, in this particular graph we have how many vertices? 1, and they are labeled as vertex 1, vertex 2, vertex 3 and vertex 4. So 4 vertices are there in this particular graph. Okay, and this is a directed graph having all the positive weights, but Floyd-Warshall algorithm can be applied to a directed graph having the negative weights also. Okay, so first one is the d0. We have to find out the distance matrix 0. This is nothing but the d0 means you are not taking any intermediate vertices. For example, this from between 1, see, first thing is from 1 to 1 diagonal elements are all 0. This is first thing. First step is the diagonal elements are always 0. It simply means from 1 to 1 this is 0. Now see, from 1 to vertex 2. Now when you want to fill this value 1 to 2, then you look at the graph 1 to 2. If is there any edge? If there is a edge, direct path between vertex 1 and vertex 2, then we'll write the weight of this vertex, this edge is 8. So we simply write 8 here. If there is a no direct path from for example from this node 1 to node 3, in this graph from this node 1 to node 3 there is a no direct path. In that case we mention here infinity symbol. Okay, it means there is a no direct path available from this. From 1 to 4, see, this is your vertex 1 and this is vertex 4. From vertex 1 to 4 there is a direct edge having weight 1. Okay, so we'll put 1 here. You got my point? So this way you find out the your distance matrix. Okay, we'll take one more row. So for example, 2 to 1, vertex 2 to vertex 1. See here, this is vertex 2 and this is vertex 1. There is a no direct edge from vertex 2 to vertex 1, so we put a infinity symbol here. Now so from vertex 2 to 2, because it is on the diagonal element, it is 0. From vertex 2 to 3, see they here, it is vertex 2, it is vertex 3. From 2 to 3 we have a direct link and having weight 1, so we'll put 1 over here. From 2 to 4, see this is vertex 2, this is vertex 4, there is no direct edge from 2 to 4, so we simply put a infinity. So this way we complete the distance matrix. Now then we need to complete find out D1. D1 means, now see these are the your nodes 1 2 3 4 vertices, and these are 1 2. Now the first step is, again, diagonal elements are same, diagonal elements are 0, so it is 0, we'll put them 0 0 0 0. Now when we find out d raised to power 1, d raised to power 1 means this value signifies that now we are calculating the path between every pair of vertices using node 1 as a intermediate node. Okay, as a node 1 as a intermediate node. Second thing is, see, first step is that the diagonal elements are 0. Second thing is that once you are calculating D1, then D naught will be considered at the base matrix. Okay, and from this, when you are calculating D1, D naught will be the base matrix, and the first row and first column will be copied as it is from the D naught. So first row is 0, then we have 8, then we have this infinity, and then we have 1. And similarly in this case we have infinity, we have 4, and we have infinity, this. So when we are calculating D1, the first row and first column will be copied as it is, or you can say these are our working row and working column. Okay, then I need to find out this value. Now what will be at this place? See, this is the formula, d of ij. This particular case is d of ij, means you have to find out d of 2, 3, distance between node 2 and 3, distance between node 2 and 3, and using, what is the value of k here? K is the 1, using the intermediate node 1. Okay, so how we'll find it? We'll find out using minimum of see, d of ij means d of distance ij is 2, 3, and कहाँ पे देखना हमें? k minus 1. Here k is 1, 1 minus 1 is 0. So मतलब क्या? D0 matrix हमें देखना पड़ेगा. Okay, comma, D0 matrix देखना, comma, d of ik, what is the value of k? K is 1, means we are looking from 2, 1 in D0 plus d of what? Kj. What is the value of k? K is 1. And j in our case is 3, and if we are k minus 1 is it will become 0. Okay, so this what? So in this case means this term and this term, these two, whatever the minimum of these two will put over here. See, now D0 means you have to look into the D0 matrix, and we'll see the path between 2 to 3. See, path between 2 to, from this is the vertex 2 and this. See, path between this vertex 2 to 3 is 1. So first value will be 1. Okay, comma. Then now this is this term is actually, we find out the path between 2 to 3, but using 1 as a intermediate path. We first go from 2 to 1 and then go from 1 to 3. So 2 to 3 we go, but indirectly using the 1 as a intermediate node. So see, from 2 to 1, 2 to 1 is infinity, 2 to 1 is infinity, plus, and 1 to 3, see this is in 0, 1 to 3 is infinity. So 1 infinity plus infinity is infinity. So we have 1 comma infinity. So what is the minimum of these two? Obviously 1. So we'll put 1 over here. Okay, so we'll put 1 over here. So this way we calculate all the terms. So again, let's suppose what is the value of this term? This is between 2 to 4. So 2 to 4 means we need to find out this, what is the minimum direct edge? 2 to 4. See here in this particular D0, 2 to 4 we have a infinite value. So we have 1 is the infinite, comma, 2 to 4. Now we'll see 2 to 4 using 1 as a intermediate. See, from 2 to 1 you'll go, what is you have? You are having infinite plus 2 to 1 and 1 to 4. See, 1 to 4 is 1. So infinite plus 1 is equal to infinite. So it doesn't matter. Minimum value is infinite only. So we'll have infinite here. Now let's see. What will be the value at this place. Now this address of this is, we have to calculate now D1, 2, 3 and 2, means from node 3 to node 2. So what we need to find out, one is the direct weight. Direct weight in this case is this, from 3 to 2 we have, one is the infinity. Direct weight is, there is no edge. Then we will see if there is a indirect node, indirect path using intermediate vertex 1. See, from we have to go from 3 to 1 first. So 3 to 1 is 4. We'll see 3 to 1 is 4 plus 1 to 2. 1 to 2 in this case is 8. So 3, this is equal to, minimum of this value is 12. So we simply write 12 at this place. Now find out this 3 to 4. When you find out D of 3 to 4 using intermediate vertex 1. First look at what is the direct value between 3 to 4. See, this is 3, this is 4. So we have a infinity here. Then from 3 to 1 first. 3 to 1 is 4, and then 3 to 1 and 1 to 4. Then here we have plus 1. So it is, minimum value is 5. So this must be updated with value 5. Okay. So this is how we'll complete this particular D1 matrix. So these values will be will come your 2 and then 9, and then finally this is already 0, right? So now using this D1 matrix, we'll calculate the D2. Now from 0 is the distance matrix. D1 is nothing but when we have calculated all the path using node 1, vertex 1 as an intermediate vertex. Now we'll take D1 as a base matrix and take vertex 2 as an intermediate vertex, and then again calculated the shortest path between all this. So now this is the earlier which we have calculated in the last step. So D1. Okay, now we have to calculate D2. Now value of k is 2, means we now find out the shortest path between all pairs using this intermediate vertex 2. Okay, and using the same formula. For first step is again the your diagonal elements will be 0. Second is when you are calculating the D2. Okay, from D1 will act as a base matrix. Second thing is that the second row and second column will be copies as it is. Okay, so we have a 8 here, we have 12 here, we have 2 here, and it is infinite. This is again 1 and this is infinite. Okay, infinite, 0, 1 and infinite. Okay, so this we will copy as it is, right? Now we have to calculate all these values. What will be this? Now again using the same formula, that see, first we will see what is the, we have to see this is actually distance of 2 using between 1 and 3. So how do we find out? We find out the minimum of what? Minimum of what? D, this is 1, and between 1 and 3 this is the direct edge, and then what is D1, 1 to 2 plus D1, it is 2 to 3, means we are taking 2 as a intermediate vertex. We have to look for 1 to 3. First we see what is the direct edge weight, and then we'll see what is the indirect edge weight which goes through the intermediate vertex 2. Okay, so in this case we'll look at this D1. So in D1 between 1 to 3 the weight is your infinite. Okay, and then from 1 to 2 is what? 1 to 2 is your 8. 1 to 2 is 8. Then 1 to 2, and what is 2 to 3? 2 to 3 is your 1. So 2 to 3 is 1. So what is the minimum of these two? Minimum of these two value is equal to 9. So we'll update this value with 9. So 0, 8, 9. Right. Now what about this next? This is 1 to 4. So again we need to find out, one is the direct link. So one is the direct means 1 to 4, and we look here 1 to 4 we have 1. Minimum value is here is 1 comma, and then we'll see what is from indirect means using 2 as a intermediate vertex. So 1 to 2 and 2 to 4. So 1 to 2 is 8. In this case 1 to 2 is 8 plus 2 to 4 is infinity. 2 to 4 is infinity. So in this case, minimum value is 1. So we do not update it. It will remain same. Okay. So similarly, we'll update the other. We'll calculate all other values. Okay, now next step is we have to calculate D3, right? D3 means now we have to find out all the intermediate, all the shortest distance between every pair of vertices using node 3. This is value of 3, using node 3 as a intermediate node, and using the same logic. But when we calculate D3, our D2 will act as a base matrix, and while calculating D3, the row 3 and row column 3 will be copies as it is. So row 3 will be 9, 1, 0 and 3. Sorry, column 3, and row 3 will be your 4, 12, 0 and 5. So these values will be copied as it is. Now see, next step is diagonal elements are always 0. We'll keep them as it is 0. See, then we say, let's suppose we have to find out 1 to 2. Now first we see how do we find it? Using this same logic, we find out the direct path between 1 to 2 in the previous matrix, means in this case it is D2. So 1 to 2 we have to find out. See this, we have to find out minimum of 1 to 2. Now from vertex 1 to 2, what is the direct path? Here from 1 to 2, here direct path is 8. So we'll have 8 here, comma, and then between 1 to 2 indirect path using vertex 3. So you have to go from 1 to 3 first. 1 to 3, it is your 9. 1 to 3. See, we have to go to 2, but we are now going to 2 using intermediate vertex 3. So we first go 1 to 3 and then 3 to 2. So 9 plus 12. So what is the minimum value of these two? Is equal to 8. So this value does not change. It will remain 8. Okay. Similarly, this 4 value. First, we have to find out between 1 to 4. Between 1 to 4, first value will be direct path will be of cost 1. Then from 1 to 4 हमें जाना है. हमें करना क्या है? अब indirect path देखना है. 1 से 3 जाओ पहले. 1 to 3 you have 9. See there. 1 to 3 you have 9, and from 3 to 4. From 3 to 4 you have 15. So it is 9 plus 5. So minimum of these two is 1. So this will also not be updated. Okay. You got my point? So now let's see one more from 2 to 1. So from 2 to 1 you have to find out this. From 2 to 1, is there any direct path? From 2 to 1 we have is infinity. Then from 2 to 1, 3 and 3 to 1, because now 3 is the intermediate vertex. From 2 to 3 we have 1. 2 to 3 we have 1. From 3 to 1, from 3 to 1 we have 4. So it is equal to 5. So here we'll put a 5. Okay. So this value is 5. Let's calculate this also. From 2 to 4. See, 2 to 4, earlier we have infinity. From 2 to 4 we have infinity is the direct cost, and from 2 to 4 using vertex 3. So from 2 to 3 we'll go first, it is 1, and then 3 to 4 it is 5. So minimum of these three is 6. So 5, 0, 1 and 6. Okay. So it is 5, 0, 1 and 6. So these values. Similarly, we'll calculate these two terms also, and they comes out to be 7, 2, 7 and 2. You will calculate using the similar logic. Okay. After now we have taken vertex 1 as a middle element, vertex 2 as a middle element, vertex 3 as a middle element. One more vertex is left, that is vertex 3. Now when we vertex number 4. Okay. When this is the earlier table which we have calculated. When we calculate D4, because now we are taking vertex 4 as the intermediate element. Okay. Then what we have to do is the fourth row and the fourth column need to be copied as it is. So we'll copy it 1, 6, 5, 0, and here we have 7, we have 2, we have 3, and this 0 is already there, and all the diagonal elements are also 0. Okay. Then rest of the values we need to find out. This value calculated. Like now, let's suppose from between 1 to 2, you have to find out what value is this. So what you do is you will find out minimum of 1 to 2. 1 to 2 direct path. What is the cost is? Cost is 8 in this particular case. So we have 8, comma, then the indirect path using the intermediate vertex 4. Means from 1 to 2 you have to go, but using 4. So 1 to 4 you have 1, and then from 4 to 2 2. From 4 to 2 you have 2. So it is 1 plus 2. So which one is the minimum value? So in this case minimum is 3. So I will update this value as a 3. Okay, from 1 to 3, let's suppose 1 to 3, 1 to 3 I need to find out. So 1 to 3, what is the cost? 1 to 3 in this case cost is your 9. And then indirect cost is, means we have to go using 1 to 4 is 1 plus 4 to 3. You have to go 1 to 3, but using intermediate 4 to 3 is your 3. So in this case minimum value is what? 4. So this value is also updated with value 4. Similarly, you using the same formula you will calculate all other values also. If they comes out to be 0, this is 5, 4, 3, 0, and it is 7 and 2, 4, and then 1, 0 and 3, 1, 6, 5 and 0. So this is your actually the all pair shortest path matrix. This is your answer. Okay, now you want to find out the shortest distance between any pair of vertices, then you can use this. For example, let's suppose I want to find out what is the shortest distance between vertex 1 and vertex 2. See, if you look at this graph manually, then see shortest direct path is 8, but the indirect path which is smallest in size is using this path from 1 to 4 and 4 to 2 is cost is 3. Now let's see what this Warshall algorithm gives. You have to go from vertex 1 to 2. See this, this is vertex 1 and this is vertex 2, and what is the answer in this particular case? It is 3. So this way, this is the shortest path matrix, all pair shortest path matrix given by the your floyd Warshall algorithm, right? So in this floyd Warshall algorithm we can have the path matrix also. Path matrix actually gives you the series of nodes which constitutes the shortest path from the starting vertex to the end vertex. See, this matrix actually gives you the length of the shortest path, cost of the shortest path, but the path matrix gives you the intermediate nodes which lies on that particular path. Okay, now the path matrix store the last vertex visited when you go from I to j. Now see, this is the basic criteria actually. The path of ij is equal to k means that the shortest path from vertex I to j, the last vertex on the path before you get to the vertex j is k, the immediate last vertex, okay, before you reach to j. Okay, so path of ij, based on this definition what we have said earlier, we must initialize the path matrix as this, that path of ij is equal to I if I is not equal to j. Okay, and there exists an edge from I to j, otherwise it is nil, right? So using this definition we can create path matrix for at every step. When we calculate d0, d1, d2, d3, d4, then we calculate the path matrix also, p0, p1, p2. When there is a no direct path available, then we say nil, otherwise it is equal to 1, and we actually mention the last node visited. Okay, now last node, immediate last node which is visited while we reach the node k. Okay, so this way, this is like example of path matrices which we calculated, p0, p1, p2, right? Similarly, for every d0, d0, d1, d2, d3, d4, we have calculated the path matrix also. Now see, this is the distance matrix which we have calculated using the floyd Warshall algorithm, and this is the path matrix which we have calculated using the earlier discussion. Now see, if you want to find out the shortest path between the vertex 1 and vertex 2, then length of the shortest path is given by this matrix. See, from 1 to 2, shortest path length is 3. But if you want to find out what are the various nodes which lies on this particular path, then you have to follow this path matrix. So now see, now from vertex 1 to 2, you want to go from vertex 1, this is vertex 1 and this is vertex 2, then first you have to go to vertex 4, means from vertex 1 you go to vertex 4, and from vertex 4 next target is your 4. So it means next is you simply go to 2, means there is no other intermediate means there is no other intermediate node in this particular path. So your path matrix is actually used to find out the various vertices which lies on a particular path, and the distance matrix gives you the all pair shortest path using the Floyd-Warshall algorithm. Now see, in this case k is equal to this, because it is a two-dimensional matrix, so n by n in this particular case, for each element we have to calculate this d of ij of k is equal to, we have to find out the minimum distance. One is the direct value and one is the using some intermediate node, right? So for every row and for every column, so we have to calculate this, right? This, and this, how many times this has to be done is k is equal to 1 to n, where what is n? N is the number of vertices. N is the number of vertices in the graph. And first step is, see, this n is the number of rows of the number of rows means as many vertices are there. This is the size of your two-dimensional matrix, and your d0 is nothing but is the weight matrix. Okay, but d0 is nothing but the weight matrix. The edge weight of the direct edge between any two pair will be placed in d0 while we are calculating this. So it is simple to say that because we have three nested loops and each loop is running from 1 to n, so it is obvious that complexity of this algorithm is order of n cube, where n is the number of vertices in the graph, right? So Floyd-Warshall algorithm is best suited to dense graph where there are many vertices and most of the vertices are connected to each other, right? This is because the complexity depends only on the number of the vertices in the given graph. No, not on the number of edges, how many connections are there. For sparse matrix, Johnson algorithm is more suitable, right? As compared to Discrete algorithm, if the edge weight is negative, then Discrete algorithm may not give you the correct result, but the Floyd-Warshall algorithm will give you the correct result even if the edge weights are negative. Okay, and the approach in this case we use is your dynamic programming approach, right? So then what is transitive closure? See, transitive closure is computing transitive closure of a graph means you want the complete information about which vertices are connected to which other vertices, if there exists a path between these two vertices or not. No matter how many intermediate vertices are there, if it is a direct path or indirect path, we do not care, but we simply want which are the vertices which are connected to each other. Okay, so input to this transitive closure is a unweighted graph. Unweighted graph means every for wij, weight of wij, if there is a direct edge, then it is equal to 1, otherwise it is equal to 0. And output of this transitive closure is t of ij. I and j are nothing but these are the vertices. If the value is 1, it simply means that there exists a path between these two, I and j. No matter what the cost of this path is, it is a direct path or indirect path, but there exists a path from I to j, and if there is no path exist, then it is 0. Now see, one simple approach to do this is to calculate the transitive closure of your algorithm, any graph is simply apply the Floyd-Warshall algorithm, and the weight or the all the edges are replaced by 1. Okay, wherever there is a path from I to j, replace that path with path weight with value 1. Okay, and make t of ij is equal to 1 whenever d of ij is less than infinity. Simply run your Floyd-Warshall algorithm. You will find out if the value of the resultant matrix from between t and ij is 1, then it means there exists a path, otherwise there exists no path. Okay, so it is simple. So what we have studied today is that we have studied a all pair shortest path algorithm, which is Floyd-Warshall algorithm, which can work with the edges with the negative weight. Okay, complexity of this algorithm is order of n cube, right? So that's all for today. Okay, thank you.